All right. Hello, class. This is Mr. Burke. I'm going to do a quick walkthrough Network Fundamentals Part 1. This lecture was given on, I think it was February 1st, but for those who missed class or want to bone up on what we covered, this recording will help. I'm going to keep it moving. Any chart that's marked as a backup, I'm just going to go past. You can go back and look at those if you're interested. Those will not be in scope for the quiz coming up, the next quiz. Okay. All right, back up the objectives. Here's the agenda. We are in part 1, so we're going to go through our architecture's topology, and then we'll get into how we isolate, segregate, segment the network for security. So this is really about our layout of the network, and then how do we manage and control network within the security within the landscape, and we'll talk about some techniques and devices and things like that. Later on in part 2 and part 3, we'll get into protocols and we'll get into some of the other specifics in terms of delivering the packets, the data packets to the end user stations. All right, this chart kind of just shows a layout. First concept we're going to get into is an architecture versus a topology. An architecture is all things in the network. It's the hardware, it's the software, it might be some processes. So it's all things in the network, people, processes, hardware, software, where the topology is the physical layout of the network devices, what connects to what. So we'll touch on that quickly, but we're probably going to focus more in on the topology. How are the connections? Well, how's the plumbing working? And at what parts of that plumbing, of that network flow, do we need security? All right. Network, simply put, you're connecting 2 or more devices and you're sharing information. The architecture is the overall design, and it has various layers, but it includes hardware, software, and any other technologies involved. The topology is how we arrange those elements. How do we physically connect it? It's the plumbing of the network. Then we'll get into protocols, but that's probably going to come up more in part 2. We'll get into a deeper dive on protocols. All right, so an architectural example is a layout can be a local area network, a wide area network, a client server. I'm not going to focus too much on this chart because we'll go through each of the important elements more in detail. But these are just how we might organize our network. A local area network is where everything is local. You're sitting right next to your peers. Your printer is near you. Everything is near you. So you may not even go out to the bigger, broader internet. It may all be just very close connections where everybody's wired together through some kind of a switch or connector. Wide area network is where we connect multiple cities together. Client server is what we're probably going to talk about the most here. That's where a device is connecting to a server somewhere, and they are sending and receiving data back and forth. That's the primary model we'll focus on in this class. And there's some other terms we'll go into later. All right, so here's some layout examples. Again, if you look at the one that looks like a star, that's the client server model where the clients are talking to a server and they're having a request and response type of dialogue. Peer-to-peer, we're not even going to cover in this class. That's kind of old-fashioned, wiring everybody's computers directly to your peers and your coworkers. That's obsolete. Don't even worry about that. I will show you something. We're going to get into it much deeper is what's called a VLAN, a virtual local area network. Essentially what that is it looks like people who work together are connected to the same resources as though they were in the same room, regardless of where they are. So for example, maybe the finance department, there's a finance person in Buffalo, in New York, in Syracuse, in Washington, in Philadelphia. They're put on a virtual local area network, a VLAN, through intelligent switches. And then they might be able to share files, get to printers, get to other resources that no one else, even sitting next to them, can get to. So it's a way to logically group people together, regardless of physically where they are. That is a heavily used approach, technology. It's all done with software and intelligent switches, so you have to be very careful how you set it up and how you protect those configurations. Okay. In any architecture, although we're a security class and we put our security lenses on, as you manage and control and deliver network services, you got to balance the cost, the performance, the availability against security. We can make a network incredibly secure, but it may be unreasonably slow. It may lack functionality. It may go down frequently, but it's secure. So you're constantly balancing all that. And I think in the network world, performance is key. Users expect, need, and want performance of the network to be, lightning fast and consistently fast. Okay. So the key concern, I would say, is also the expansion of the attack surfaces. The network is, other than people, is the key avenue, a vector for an attack. So they're probably attacking people, but using the network to get there. You're not being attacked by somebody who physically breaks into your office or comes down the chimney. They're coming from some remote location through the network, and they may be attacking you via email, via password cracking, or other techniques. But the network is one of the big attack vectors. I would say after people, network is next. All right, topology, again, that is how we do the plumbing. How do we logically connect? How do we physically connect our network devices? I'm going to go through a couple of things, but these are backup. This is kind of the old days when we used to wire everything together in the office. We're now in the wireless Wi-Fi world where things are connected. After you connect wireless, you can be connected to any resources through technology, software, and other means. So you are not physically limited to what you can get to. So these are backups. Don't even worry about star, bus, and ring. I won't ask. I will talk about what we call the network layer. How do you get from one network or get your data from one network to another network? How do you, sitting in Howard University, communicate with Amazon, Amazon.com? And you are going through a public network. You're going through the internet to connect or to transmit data and receive data. And what's behind that are routers. Routers are the devices that connect the networks together, and they're routing based on IP addresses, domain names and IP addresses. Firewalls are also used heavily in the network, and we're going to hit those hard as we go into other parts of this presentation and the next presentation, part 2. Firewalls are simply a device that sits in line in the network. It's reading network traffic and it's enforcing security policy. For example, you may have a firewall that no data coming from a .com gets into your network, or a .edu gets into your network. So it is actually reading the network packets to see, where's it coming from, where's it going, what protocol, and any other things that are available in the packet header, and making a decision, do I allow that traffic to go through or do I block it? So it's all about establishing your security policies or rules for your firewalls. We'll talk about that more later. There are other devices. I'm not going to get into these much in this class. These are more the physical, what are called data link or physical layer devices, switches, bridges, hubs. Now, wireless is a whole different discussion area. That'll be a separate module we'll go through. But switches, bridges, and hubs are simply a way to take a signal that's coming in and switch it in different directions, or split it and send it to multiple directions. So think of a splitter that might take your DVR player at home and it sends it to the TV, and it also sends it to another TV. It's simply switching the traffic. We'll talk about it later, because with intelligent devices, frequently you might have a device and it's doing switching, it's doing bridging, and it may also be a router. So it's not unusual that you have a device that does multiple things, and it might also be a firewall. So with the advancements in technology, you might have one physical device that's doing multiple things on this list. And as I said before, wireless we'll talk about separately. So I do want to point out routers. That's network to network. A switch is internal to your network. Your data is already in your local network and you're just switching, sending it down a different path. You may be switching it to your printer. You may be switching it to different users, but switching it tends to be internal to your network. Routers are going across the public network or going across a different network. Okay. So on your routers, because you're talking network to network, you want to be very careful with your access control list, your credentials or passwords to make sure those have been updated. You don't still have the default passwords in place. And there are various attacks that occur on a router. We'll talk about that in our section when we get into attacks. But the bad guys may try to go in and take control of your router. They may want to masquerade, be an imposter and get their data through or hijack data. Or they may just want to sniff or snoop and eavesdrop on the data that's passing through the router. So those are just a couple of attack techniques. Now a switch, because it's internal to your network, also you have to make sure your credentials, your passwords, and all those things are strong, but you also need to make sure you're physically protecting your switch. Your switch oftentimes may be in the office space, maybe in the student lounge, maybe exposed. It's not locked up in the basement of the data center somewhere. So it might even be more physically exposed and vulnerable than is a router that tends to be, behind multiple closed doors, locked doors, in secure areas. All right, wireless. Now, in the last section, we got into wireless, but an access point is simply how that's the thing you are connecting to when you go to Starbucks.com, Starbucks Wi-Fi or McDonald's Wi-Fi or HU Guest. You're connecting to an access point, and if you look in the room, they're sitting right there in the ceiling. They're all over the building. When we go to wireless, we'll talk about this in much more detail, but we have to protect our access points wherever they may. Also, imposters may come in, put an antenna up, and pretend to be an access point. They can broadcast from their own laptop that they are Howard student Wi-Fi, and people may try to connect to what we call an evil twin. But let's wait till we get to Wi-Fi and wireless to get into that. In our last part 1, we talked about the addresses, the SSID, the BSSID, and the ESSID. And I think you guys know what those are. SSID is the network name. That is like HU Guest. BSSID is the MAC address. That's the physical 16-character address that was provided by the manufacturer. The ESSID is the SSID, but it's used when you have multiple access points. So for example, in our building, we have access points in both, I think, just about every classroom on every floor of the building, yet they're all broadcasting HU Wi-Fi or HU Guest. So it's where multiple access points are used to broadcast the same Wi-Fi name, which is the SSID. All right. And then there's some topologies we'll get into quickly. Wireless, where you can connect hub and spoke, where all connections come into a single wireless, if you will, access point, and it connects to the internet. Ad hoc, don't worry about that. Won't even get into it. But mesh is a different implementation than hub and spoke. That's where you have many access points, and they are like a mesh. They're all talking to each other, but you only have a few, if you will, links to the internet. So every access point in the Howard School of Business doesn't have a connection to the internet. They are daisy chained together in a mesh, and then somewhere in that daisy chain is a linkage out to the internet, into the Howard network, into the internet. All right, that's mesh and hub and spoke. Okay, wireless. Again, here are some examples of attack. We're going to get into this much deeper, but I'll quickly go down. Piggybacking is when it's like somebody piggybacking when you walk in the door. So if somebody logs in, somebody's snooping and sniffing and watching the credentials, and then they'll try to use your same credentials to get on that Wi-Fi access point. For example, if you issued a password to get on an access point, they may be sniffing to see what that is and try to jump on that access point at the same time using the same credentials. Okay. Ward driving, and I'm not going to get into these deep, but the ward driving is where Let's get this later. It's not on this quiz, it's backup. All right, so we're summarizing our architectures. You can look at the components here, but I think the key takeaway on the architecture, or more importantly, the topology, is we really have to be careful how things connect together. Where are our points of failure and where are our points of weakness, and where do we have to control those? And we'll talk about that as we go through the next section. So, to control a network, to put security in a network, we have concepts that we're going to go through, including layers of defense, DMZ, which is demilitarized zone. There are different types of internet, intranet, and extranet, wireless, gas, honeynet, flat networks, and some other concepts. Let's go down through each one. Layers of defense. And you can see in the picture here, at its core, what we're really trying to protect, what is most crucial, is to protect our data. Protect our data. That's what the bad guy is trying to get to, or that's what, if we lost our data, where we have the greatest risk of the greatest damage. You see multiple layers of security wrapped around that data sitting on an application that has controls, and or under applications that are controlling it and have credentials and passwords. Those applications are sitting on a host which have controls and passwords and credentials and error logging and detection mechanisms. Those hosts are sitting in a network that also has a perimeter of controls and passwords and error checking and security alerts and all the above. So based on this, you can clearly see the network is the outer perimeter. That's the first thing that gets attacked. That's the first entry point. And that's also, at least on this picture, the weakest link. Again, people are the weakest link, but the network, if we're looking at the technology, is the weakest, most exposed link. Okay, so the point of this chart is that we to protect our data, we make sure we have security at every layer. Okay, now let's look at a topology. And I'll weave the topics in here. First of all, if you look over to the right, you've got a network and you have the internet and activity, traffic. Web browsers are coming and trying to talk to servers within the network. We have first a firewall. A firewall is a hardware, and it's usually hardware or software device, intelligent device that's reading all the traffic that's coming in, and it's making a decision. Do I allow that traffic to go through, or do I have a rule to block the traffic? And that rule could be based on the IP address it's coming from. It could be based on the protocol. It could be based on time of day. All kind of factors could come into play. But the firewall is actually reading the data, at least the packet header, reading the header of the data and making a decision to pass it through. The next concept is a DMZ. A DMZ, also known as a demilitarized zone. That concept, that term comes out of the Korean War, where there was a buffer zone between the South Korean and the North Korean troops, like I think a few miles wide or whatever. And there was an agreement that the good guys and the bad guys wouldn't send troops in there. That was a safe zone. That was a space where, if you will, approved access, travel, whatever. It's a buffer zone. So neither country would put their heavy armor or send their troops in, but it was a safe passage area. Well, that's what we have in technology, is a DMZ, a space, a buffer zone, where we as an organization are going to allow internet traffic to go to that buffer zone and talk to certain servers in that buffer zone. That internet traffic cannot get to our internal zone. We block that off. But we will allow, because we in the modern world, we have to have a web-facing server. So we have a web server. We have to be able to receive and accept and send email. So we'll have an email server, and then we'll have a proxy server too, and I'll talk about that in a second. So again, the DMZ is very important. So we have firewalled the DMZ off from the internet and allow certain traffic in, but not necessarily all traffic. We also have firewalled that DMZ off from the internal network. So we only allow a selective internal activity to get to the those servers. And the concept here is really, if something bad's going to happen, it's going to happen in that buffer zone. If a server is going to go down, it's going to be a proxy server, an email server, or a web server, but not our application servers, database servers, or where our precious data is. That is never in the DMZ. So you never have your corporate mission critical data in your DMZ. Okay. Now a proxy, just quickly, it's a go-between. It's like a broker, where if somebody on the internal zone wants to, for example, send something to somebody who's on the internet, they would send it to the proxy server. The proxy server will turn around and forward it under its IP address to the external target, external source, I'm sorry, recipient. And that way the external recipient never sees the internal's IP address or information. So it looks like it came from the proxy. So the proxy essentially, it's like a network address translator. It is the only address the external party would ever see. They'll never see the internal address or credentials. Okay. And a proxy, by the way, could work both ways. Things coming from the external world get to the proxy. The proxy may turn around and put certain credentials or information or strip information off as it passes it internally. That's called a reverse proxy. So data is, if you will, masked, mapped, and sent on its way under different identity, different addresses. Okay. VPN is the only other topic I'll talk about here. That's a virtual private network, and simply put, that's a tunnel. I think we got a chart coming up in part 2, but it is a tunnel that allows somebody who's working wherever they are to send and receive data using an encrypted pathway. Now, even if you're sitting in Starbucks, it establishes a tunnel. Even though you're going over the internet, the public network, the Starbucks network, everything that's coming in and out of your device is going through the tunnel, which means it's encrypted. All right, IPS and IDS, we'll talk about those in another section. All right, so here's our DMZ. Buffer zone, it's between the internal trusted network and the external not trusted network, but you will have selected resources sitting in the DMZ that the internet has to get to and your internal people have to get to, but you don't allow direct access from the internet to your trusted network. It is the only place that access can be received. Access or data can be received. Now we got a couple of concepts we'll hit real quick here. An organization can have multiple internets. Okay, there's the internet, which is the external World Wide Web. That is the least protected, most vulnerable. An organization may say, okay, I don't want my users to be on the internet, but I like the functionality of web applications and being able to communicate on a web. So I may build out what they call an extranet. So this is an internet with only select parties invited to participate. For example, an organization may have its suppliers on its extranet. It may have its parents of students may be on the extranet. So you give special permission to certain people to be on this network. They're not internal to your organization. They can be external to your organization, but they have permission. Okay. Then finally, you have an intranet. That's like an internal internet. It's like Bison Web and things like that, where people from the outside can never see this. You can't see it from the external network, but if you're authorized and you're part of the internal network, if you're authorized, you're on an intranet. So quickly, and going through it from a security standpoint, the intranet is the most protected. It's only internal. Extranet is like the next level up. It's internal with select external, so it's a little less secure. And then finally, the least secure is the internet. All right, I think on this one, this is other security zones. For example, how we lay out our wireless. We may decide that, for example, a guest, if you're in an office building, you may say, okay, only guests can use the Wi-Fi on the first floor in a public area, controlled area on the first floor, like the library. If they go up in the building, they can't get on the Wi-Fi. If that provides some security and protection, you basically have isolated people to use certain zones to get to the Wi-Fi, especially guests to get to the Wi-Fi. Guest zone, same concept. You just have certain places where people can access the network. HoneyNet, different topic. We'll pick this up in attacks. This is where we might have a network which is a fake network that, let's say Bank of America may build up a network, and they want a place where attackers may try to attack. So they can see what tactics, what the attacker's doing, but in fact, it looks real, but it's fake. So again, a honeynet is to attract attackers. You can then observe, monitor, or you can go after them. You can turn them in. So it's very popular, especially in the intelligence world. And then a flat network. I think we have a chart on that. No, we don't. That's where instead of having multiple entry and exit points, everything goes through a single switch or access point. So you funnel all your traffic through, if you will, a single path as it goes in and out of your network. It might reduce costs. You don't have as much redundancy and duplication in your network, but you are maybe less secure. You are, I'm sorry, more secure, but less robust. Performance may be worse. Availability could be worse if that device goes down. But essentially, a flat network gives you a single control point, so you can observe, monitor, control all traffic coming in and out of your network. Okay. So network separation, segregation, isolation. A couple of ways to do that. We may want to subdivide our network up physically or logically to provide more control. For example, maybe Howard students, part of the network you can get to, but you can't get to the faculty network. Faculty can't get to a research network. There may be sub-networks within the greater network that are isolated and segmented in such a way to provide additional security. So we'll talk about physical separation and logical separation. All right, enclaves, I marked this as a backup, but simply put, it's where you may have equipment, devices, resources in clusters, and they are controlled appropriately. You may have a security cluster, a database cluster, management servers, but that's not unusual in database environment, in a modern technical environment, that they have clustered the servers, and then they control them appropriately. I have this marked as backup. I'm not going to go there on a quiz or an exam. Okay, an air gap is a physical separation seen in the intelligence world, especially where you have a top secret operation. First and foremost, you have to have tight physical control on the space. So a top secret operation may have additional locked doors, cameras, security guards, procedures of signing in, signing out, things like that, biometrics, fingerprints, eye scans, things like that, to even physically get in there. Now, once you're in there, the network is not connected at all to the external network. It is completely separated, so there's a lot of redundant equipment needed when you have a kind of a completely self-contained top secret controlled network. So it goes without saying that network cannot get to the internet. It is completely independent of the internet. All the resources you need are right there in that room, or isolated for you. So that's an air gap. That's where there is no connection between the external network and your internal network. High security. A couple of exposures. In that environment, they would be careful that if somebody who walks into it's called like a vault or a SCIF, the secure area, and they bring a USB. And maybe just for convenience, say, hey, I want to do some work at home, so I'm going to dump off some files onto my USB. I'll go home. Now that data is now exposed, it's left the secure area. They are also concerned about back doors, where for convenience, when people set things up, sometimes they'll put a little what's called a backdoor, but a way maybe for the programmers, the people who do maintenance on the system, to bypass some of the credential and security controls and maintain the code, fix code, things like that. And then more than anything else in that environment, anything that would result in a data leak, anything that would result in a data leak has to be watched. So they may have additional sensors in place because they don't want you to come in there and bring a mobile phone and start taking pictures. They don't want you to come in and have a copier there where you could copy files into hard copy and walk out. So anything that could result in a data leak has to be controlled in an air gap environment. All right, a virtual LAN. We talked about this earlier. This is a way for people who are physically in different places, and they're physically in different networks, but we can connect them together as though they're on the same network. So all the finance people, regardless of where they are around the country, they may come in on a virtual LAN and they can all talk to each other directly through their workstations. They can get to the printers and the file servers that only they can see. They may have certain servers that only they can get to. So a VLAN is a way to logically connect people based on their identity, wherever they are, to certain resources. So it's pretty sophisticated. It's widely used, and because of its sophistication, you got to make sure you really control it. Okay. All right, I think virtualization out of scope. We'll talk about that in a separate session. Zones and conduits. Okay. All right. This goes back to that term when we talked about a flat network. By separating and segregating your network into certain zones, you can control the input, the access points, and the exit points of data, and maybe you force it through a conduit, a tunnel, a path that can be managed and secured. You don't want multiple ways in and out of your network unless they are controlled properly. And then zero trust, I kind of threw it in here, but that's a concept where wherever you are, when in doubt, ask people to re-authenticate. If you are about to go from server 1 to server 2, they may be identical servers, they may be in the same cluster, in the same zones and things like that, but go ahead and ask them to re-authenticate. Put your user ID and password in so we can make sure it's you. So zero trust is forcing a re-authentication when in doubt, when anything changes, when something, maybe even every hour, we'll ask you to put your password back in, re-authenticate. Okay, so the users don't necessarily like that, but it's a way to ensure security. Okay, tunneling. Okay, we're going to talk about virtual private networks in a second here, but tunneling is a method of forcing your network packages through an encrypted tunnel. So it's not encrypted at its entry point. It's immediately encrypted and it's passed through a tunnel. The tunnel may by travel across a public network, but it's going to be all garbage. It's going to look like encrypted data. All right. Encapsulation is a term, we'll pick it up in the next section also, where you take data and you can encapsulate it within other data. So it's like taking a small envelope, putting it in a big envelope, and putting an address on the big envelope. Take the big envelope and put it in a box, put an address on the box, put the box in a bigger box and put an address on that, and send it on its way. And it goes through multiple layers of technology, network technology. The first layer may say, I only care about the address on the big box. Then when it gets to its next transfer point, they may open the big box. I only care the address on the little box. And then it goes on, they open that up and they look at the big envelope. I only care about the address. So each layer of network technology is only concerned with the addressing information they need to pass it to the next step. But that's encapsulation. We'll talk about that when we get into protocols. Then finally, a virtual private network. We talked about that earlier. That's simply where you can connect from a device going through an encrypted tunnel but you're sending that data over a public network. So you're sending your data over the internet. You might be sitting in Starbucks, but your data is immediately encrypted and decrypted on each end of the tunnel. Okay. I think this is one of the final things we'll get to. As we talked about these various devices like firewalls and various other technologies we can use to control the network, one concept comes up is what do we put in line on the network path and what is out of bounds. So inline is something that sits right in the middle of the network and it's reading the data, the network packets, the network packet headers that are coming across and making a decision to let it go through or not. That's like a firewall. That may slow down your network traffic because it has to process, view, and make decisions on all the data. Out of bounds is where you have a device and it's not sitting directly in the path, but it can be outside the path. And as the data passes, it's monitoring. It might be copying. It might be creating logs of what's passing. And that data then will be acted on after the fact. So you are not blocking anything, but you have data that can be used to process alerts or to put out reports and measurements and it may even put an alert out, hey, there's something fishy going on, but it's not stopping the data from passing. Okay, and examples of that, there can be sensors and collectors and firewalls, and you have to make a decision. Are you putting those things in line or out of bounds, out of band? Okay. All right, so I'm going to go to the next chart. The top of this chart is the only thing to be concerned with. Don't worry about the stuff under other load balancers, DDoS, and aggregation switches, but we've talked about proxies. That's a broker that's in between servers or systems, and it acts as a go-between. Firewalls we've talked about. We'll talk about that some more. And VPN we just talked about. So those are the three concepts I want you to come away with. And inline and out of bounds and out of band. All right, we're at a backup. We're done with this section where these are references, also backups. And that's the end of part 1. So thank you for your time. I will close this out and we'll see you on the next video.